I want to start today's video off with a question. How many real numbers are there? Well, as you probably know, there are infinitely many. And for us as humans, this is okay. But for a computer, infinity is quite a tricky concept to deal with. So we need some way of representing these numbers in a finite manner. As you've undoubtedly seen before, there is a way of representing every natural number as a binary number. So here, for example, we have the representation of 13 as the binary number 1010. And here we have the corresponding representations for 2 and 702. But this way of representing numbers only works for the naturals. So we can't deal with fractions, we can't deal with negative numbers, and we can certainly not deal with irrationals. So for those numbers, we need something a little more clever. And that thing is floating point representation. So on the screen right now, we have a visual representation of 32 bits. The 32 bits that we're going to use to represent real numbers. So how does this representation work? Well, firstly, we reserve one bit for the sign. So whether a number is positive or negative. Then we reserve some bits for the exponent. You can think about this part as where the decimal point is placed. And finally, the real meat of the representation is in the mantissa. Now, for this short video, we're not going to get down and dirty with the details of the mantissa, but suffice it to say that these three parts combine to form the floating point representation of a number. So let's look at an example. Take the following floating point representation. Well, we know that it splits into three parts. The part that tells us the sign, the part that tells us where the decimal point is placed, and finally the mantissa. So in this case, by some clever manipulation, we see that the representation corresponds to the following number. The people who invented this system were in fact very clever, and they figured out a way to save a bit of space. It turns out that the representation of the mantissa always starts with a 1. Yes, even for this number. So by only representing this part in the mantissa, they save a bit of space. And I'm sure some of you guys are screaming at your computer right now, because I just said the representation of every number begins with a 1. But there is of course one number for which this is not the case, namely 0. So 0 is one of those special values that we need to treat separately in this system. And we need to give a special representation. So in the case of 0, this becomes the string of all zeros. And this leads us to another special value, namely the one that you get when you divide a number by 0. Then you get infinity, which is represented as follows. And we actually represent minus infinity simply by flipping the sign. And the final special value I want to mention is that of not a number, which is what you get when you divide 0 by 0. This is represented by a string of all ones. So, as we've seen, we can represent numbers from the very small to the very, very large. And you might at this point wonder, well, how large can we go? I mean, we saw there are infinitely many real numbers, and we can go infinitely large there. But can we represent arbitrarily large numbers in this manner? Well, no. The floating point representation only has a finite amount of space, so we can only represent up to a finitely large number. And, well, you really don't want to go larger than that, or you might face some catastrophic consequences. And you might think I'm exaggerating, but in 1996, a space shuttle crashed at launch due to a floating point arithmetic error. So be warned. We want to encourage you guys to think about this topic more, and because of this, we're giving you some homework. Why don't you try to see if you can implement floating points representation yourself? If you want some hints, or if you're just interested in learning some more about floating point arithmetic, here are some resources. Thank you guys for watching. Catch you on the flip side.